thank you very much for the introduction and also for the invitation to talk here. And this invitation is actually based on a talk that I gave at the International Supercomputing Conference a while ago. And I actually decided to really use the same slides because I think they do fit very well here. And this was also the request that I talk about that topic here. But I'm happy to I'll fold in one or the other of our current research aspects. So there was also a quick overview of my background. Yes, I have fond memories of studying at Erlangen University. I was employee number 1 of the newly established graphics lab there, which is now led by Marc Stamminger. And Tim Weyrich also joined in Erlangen, who I know very well. It's great connections. We still have connections. I still have connections, or we have connection with each other, I guess. What is maybe a little bit interesting for my talk today is that I have a background. I actually originally studied physics, but at the end of my studies, which was in Tübingen, and I finished that in Tübingen, I already moved over to computer graphics, and then started to work in AI only in 2008 when I joined as a scientific director at the German Research Center for Artificial Intelligence, and I'll say a few words on that in a second. So my background really is fairly broad, right? In particular, what I will be talking about today is the mix between computer graphics and AI, and I hope that I can motivate why that is an interesting topic. There's a really strong and good feedback between the two. I should also mention that I'm a member and one of the PIs in the NHR Southwest, which is operated by Saarbrücken, Kaiserslautern, Mainz, and Frankfurt, where I'm part of the method lab on compiler and the method labs on compilers and AI. So with that, let me go forward. A few words on my background. So the DFKI is the largest independent research center for AI, actually founded almost 35 years ago. So for a long time, it was like the main or probably the only really major AI organization or research organization of its kind. We now have 6 sites in Germany. Saarbrücken and Kaiserslautern were the original ones. Now, then Bremen joined. Mid of last year, we had a double site in Osnabrück-Oldenburg joining, and Berlin, Darmstadt, and others are involved here as well. We have a number of research areas that cover essentially all areas of AI. We have competence centers who write for specific areas like deep learning and autonomous driving, where the different research areas are working together. And the number of research people actually is over 1,500 by now. So, and we've been growing quite a bit over the years. A few words on DFKI. We are a little bit unusual in that we are a private company. We're a GmbH, a non-profit GmbH under German law. The shareholders are the universities at our main sites, but the majority of the shares is with the industry. You see this here: Google, Microsoft, SAP, Intel, NVIDIA, many other of the big IT companies. We have many smaller ones as well. We have the agricultural domain, we have the retail domain, we have finance and insurance, and many others. We really cover, in that sense, we cover the area of applications very well. And that is also the main mission of the DFKI, is that we take the AI technology, we keep further developing that with a focus on the application areas and the transfer to industry. But as you all know, AI is moving extremely fast. And so for many of the applications, we actually have to go back and work on the what we call application-inspired basic research. So the basic research, not because no one has done this yet and we can publish a nice paper, but because we need to do it in order to actually do the application research and then transfer the results to companies, to our shareholders, and spin-offs in particular, right? And we work very closely with the Max Planck Institutes, for example, here on campus, with the universities at our main sites, and many other partners in all the different areas. So one of the key areas that we are pushing into is what we call trusted AI. And I'll talk more about this. So the idea is, how can we provide guarantees? How can we provide guarantees for AI systems, right? And my group here at DFKI is tracking that, or is contributing to that topic through three main areas. The one is what essentially AI technology, right? How can we design AI system that can ideally inherently provide these guarantees just by design? Or how could we develop external tools that help us provide such guarantees if the algorithm don't provide them by design in the first place? The second area, and this is a very close link to the graphics area, is how can we use synthetic data that we generate from parametric models, specifically in the area of autonomous driving, through simulation? How can they be used to train AI systems, to validate AI systems, and eventually really to certify AI systems, because we can systematically provide guarantees that they are safe, right? And all of that needs to be supported by AI platforms and high-performance computing, because specifically, right, when we do those simulations and synthetically generate data, that's a lot of compute that we need to do there. But also a lot of the AI processing is obviously very compute intensive. And so we need to provide that infrastructure in a reliable and very efficient way. And I'll talk a little bit about some of the compiler work we're doing in this direction. So what have we been, so a little bit of background of projects we've been doing. This is actually a somewhat older project. So the steelworks at Völklingen, actually not far away here from the university, from the DFKI site in Saarbrücken. This has continuously been run by a multi-agent system designed here actually by my group for 24/7. This entire plan, the control of what process is being triggered here in order to save time, to save energy, and many other aspects. That's really, so AI is not just some Google thing, right? It's really contributing to the big industries in Germany with this example. More on the graphics side, we've done a lot of work on real-time ray tracing. This is a technology that we majorly helped develop in the beginning of the 2000s. This is a technology that now is provided in terms of tools and products by NVIDIA with AMD and also Intel, the Embry toolkit, a real-time ray tracing toolkit. And that toolkit actually was widely used in the film industry and actually received a technical Oscar beginning of 2021. So, I mean, right, it's not often that researchers can get Oscars. There are a number of Oscars that went to the graphics community. So that's one of them. Graphics is one of the areas where you can actually get an Oscar for your research, which is very nice. Also, we worked on the hardware side, and in 2005 actually published a ray tracing hardware design implemented on FPGAs. This is where a little bit of the FPGA work that I'll briefly talk about comes from, where we showed the first fully programmable ray tracing processor And it turns out that NVIDIA, 13 years later, actually started shipping products with a hardware ray tracing on their GPUs, essentially on all their GPUs since then. And in the meantime, AMD and Intel are doing the same. So this is really being implemented in essentially all GPUs today, which is quite interesting. And lots of work that will also link back to AI is that this real-time ray tracing and also the ray tracing hardware has helped dramatically to improve the simulation aspects for lighting simulation, so on the optical sensor, including the sensor models, but also on the radar side. And a lot of the technology we developed here are now part of really commercial rendering products like RenderMan from Pixar or V-Ray by the Chaos Group and many others. So it's really this practical aspect of really developing new tools, new technology, new algorithms, and then making sure they actually make it into products, right? Other areas we're working in is here, for instance, Industry 4.0 and collaborative robotics with companies like Volkswagen and Airbus, that will be a part of my my presentation today, specifically looking at autonomous driving and specifically in the context of how can we have realistic models and using training, using synthetic data, as I mentioned it before. So this is one of the examples here. So let's step back a little bit and to see where we are in terms of AI, right? There's obviously many, many success stories on the hardware verification side, right? Some of you might remember the Intel FDIF bug that cost Intel a fortune when it happened. That's 25 years or more ago by now. Of course, we had an exponential explosion in the complexity of our chips. But this kind of error, at least, didn't really show up at any major scale since then. So that's a huge progress. And this hardware verification technology actually is deeply linked into AI technology, comes out of the AI technology. But also huge knowledge graphs, tremendous progress on research, on search and optimization. Only that really enabled Go Play, made it even possible to get good Go Play going, right? So there's a lot of stuff, obviously the whole ChatGPT stuff that's working now with these transformer models. So huge progress, a lot of that through deep learning, of course. But we see this shift away from, not away, I mean, there's still a strong focus on deep neural network, and that will stay there. But there is a additional shift to what we call here in Saarbrücken neuro-explicit technologies or models, where we combine explicit models like differential equations, simulation codes, things like that, symbolic AI, and combining this with pure neural networks, which typically only can do approximations, really good ones often. But one of the key issues of ChatGPT, for example, now is, yes, it can talk very well, but it's not always clear that what it talks about is actually true. So the grounding for what these AI systems actually operate on is often not there, and that's really something that we're trying to address with our trusted AI approach, right? And we have still severe challenges in this area, and I'll talk about this. And these challenges actually have very severe consequences on the practical use of AI. Before I get there, I want to kind of share and kind of get us on the same page in terms of where we are with AI and how the AI area is really structured, right? So AI really is a very broad term for a lot of different techniques, and we can broadly classify them into reasoning techniques. This used to be rule-based systems or statistical reasoning later on, and alone on this side, right, we have dozens of techniques that do certain kinds of reasoning, statistical, rule-based, many other techniques. So there's really a huge toolbox of technologies for certain kinds of problem, right? And then on the other side, we have learning, machine learning. There's reinforcement learning, there's support vector machines, and many others, again, dozens of tools, right? One of them, a really important one, is deep learning. But one thing I want to really get across here, that deep learning is not the same as AI. It's an important, really important part, don't get me wrong. But it is one part of the toolbox that we have. And like with any toolbox, for each problem, you need to use the right tool. And what happens now is that we're looking into these hybrid or hybrid AI techniques, right, where we combine different AI techniques with each other, right, in particular more explicit models with, for instance, deep learning. And one development is that we're not just combining AI models that are within this hierarchy here, but we're now starting to combine them also with techniques from other areas like computer graphics, right, where we have computer graphics models and simulations. And I want to talk a little bit more about how we can combine machine learning and AI with these explicit models, right? And again, we call these neuro-explicit models, right? And of course, then there are these applied communities that talk about vision, languages, robotics, and many other areas, and then the application areas. But that's just for completeness here. So what are these challenges, right? It's really functionality versus robustness. The AI system that we have today are really highly capable, right? You can essentially take a camera, point this in some direction, and the AI systems we have today are extremely good at telling you a lot about what's going on, right? This is an example here, very simple example, of course, but just to visualize that. But at the same time, these systems that have great functionality and work like a charm in many cases, but we cannot, right now, we cannot guarantee that they don't make fundamental mistakes in the process, right? And I guess you all have heard about those issues, right? You put a couple of colored patches on a stop sign and, right, AI will recognize something completely different. Or you add some targeted, right, handcrafted noise, well, not handcrafted, it's adversarial AI here, but specially crafted noise to an image that we as humans wouldn't even perceive any difference in, or hardly any difference. And again, it's completely misclassified, right? And that's kind of scary, that we have a technology that does great stuff, but can be misled dramatically. And this has dramatic consequences. You probably have seen this image before. This is from the Uber accident in 2018, where an autonomous driving car from the company Uber was confronted in a dark environment with that person, this woman, walking across a 4-lane road. It was seen by the car for almost 6 seconds. But the car recognized that there is an object, but decided not to do anything. And this woman was killed by the car just as she was almost across the street, right? So it's not enough to provide the functionality that we can drive. And I would argue autonomous driving, we can do this today, right? We can drive, right? But we need to also be able to certify these systems and to guarantee that they don't just kill people once in a while, right? Functionality is not enough, but we need to make sure that they are robust and that they don't just make mistakes in situations where, right, they can't deal with. And eventually we need to define standards, right? That's not a technical aspect. Well, it's also a technical aspect, not alone. So we need to define the standard with which, like, what is good enough autonomous cars, for example, what is good enough AI to address to be allowed to be sold to the public, right? And you all know about the AI Act that tries to address this going forward. So the we have or what's the problem behind all that, right? The problem is that our world is extremely complex, right, in terms of the shape of objects, the appearance, right, the texture, the color, the motion of objects, weather phenomena, right? Wet objects, wet streets look very different than dry streets. Complex environments where many cars, pedestrians, bicycles, and so on are moving fast among each other, right? And in these AI systems must make very reliably, must make accurate decisions, right, despite this extreme complexity, right? And they need to do that even in very extreme and critical scenarios. And again, for the rest of my talk, I'll talk about I'll use the example of a kid running in front of a car, right? This is exactly the case where we really want to make sure that the car does whatever is physically possible, right? At some point, physics might not allow the car to brake or avoid the crash, but if it is possible, the car should make sure that it finds the best way to avoid harming the kid. But here comes the catch, right? For exactly that critical situations, right, we luckily don't have data, right? And I think we're lucky to have no data because that means we are not hitting kids that often. And so we have little data. And we don't want more data, right? We don't want to send 150 kids in front of cars just to get data to be able to avoid that. So how do we deal with the case that we want to really make sure that these situations are safe? And what we're doing here and what we're advocating, we've been advocating this for many years now, is the use of synthetic data, right? So simulating the data from virtual models. And it actually turns out we are doing this in other areas very extensively, right? For crash tests, right? You might think that car companies still crash lots of cars against walls to make sure that they're safe. But that's actually not really true because almost all of the crash tests are being done in a computer now through finite element and other simulations. And the car companies essentially only crash cars at the very end, not to make sure that the car is safe, but to validate that the simulations that have been done are actually correct, right? So it's really virtual crash tests first, and then just the validation of that. And that you see this also in the area of autonomous driving. So initially, the car industry that tried to address autonomous driving thought that all they need to do is just gather enough data from reality, right? So you have a car, you have that reality, you gather lots and lots of data, you drive millions of miles, right? And yes, and that is exactly, that was the problem. But you still see people argue for that today. This question like, how many million miles do I have to drive in my car to have a safe car, right? And that's obviously bullshit, right? Because that is exactly that. Essentially that's asking the question, like, how long do I have to drive until I've hit enough kids, right? So I have enough data to avoid that in the future. And I think we all agree that, nope, that's not the best way to develop AI systems, right? And so it took the industry a while to realize that. I hope that, I think I can argue that we've been at least part of this push towards we need to work with synthetic data, right, given the right platform, we could essentially scale and generate as much, right, if we had good models, we could generate as much data as we want. But the question is, where does the data come from, right? And it turns out that the models, that the systems that they're using, even today, are mostly computer game technology, right? And a lot of the models are often also computer game models, for instance, for pedestrians and other data. And you could argue, well, they look really good, right? Actually, the first paper that was published in this area was using a car racing game, GTA 5, and grabbed the screen to use that as training data. And while these games look really good for gaming, I think we can all argue that they are not very realistic, right, compared to images you take with a camera outside while you're driving. So the question is, how can we address that? How can we address that? And this is where digital reality comes in. This is what we call our approach, and I want to go quickly through that approach here. That's a 4-step process. The first one is we use AI to take data from reality, not necessarily these critical situations, but generally, like the motion of pedestrians in general environments, the models about other geometry, other materials, behavior, motion, complex environments, and so on. Models of bikers, pedestrians, things like that, all the people you typically see and objects you typically see in traffic environments, to stay with the autonomous driving example. And then in the second step, we are putting together these partial models of objects in reality and model certain relevant environments, in particular for critical situations, such as a kid running in front of a car, right? So you need a kid, you need cars, you need streets, you need whatever is around that, and so on. But however, there are obviously many thousands, if not millions, of different configurations that are possible, right? That could have kids from the left, from the right, large kids, small kids at different times of day, inside a city with parked cars or no parked cars, and so on, right? There's many situations. And we need to identify exactly those situations that are critical and that would help us generate the best data for the training and certification validation process, okay? And that's actually an interesting research question, is how, from all of the possible configurations of such a scenario, which ones are the one that we should use for training? And that's actually one of the research topics that we're trying to address today. And not here in this call, but this is one of our research topics we're working on. So once we have these set of concrete instances, the third step is to actually simulate these environments. So this includes, of course, the simulation of that specific environment, so animating the humans, the pedestrians, the bicycles, the other cars, the waving of trees in the wind or whatever. But it also includes simulating the sensors, okay? Because what we want to generate, and hopefully we can generate at the end, is the data that a real car with its real sensors would see if it were in that situation, right? And as close and as realistic as possible to the real data as we can possibly make it. Yes, so that includes optical sensors, that includes LiDAR sensors, that includes radar sensors, and possibly others as well. And that's a non-trivial problem, right? Because many of those sensors that are commercially available are not open, and it's sometimes hard to actually know exactly how they're working. But we've made great progress in this area, and I'll show some examples in a minute. So once we have that data, we can now use the data for training AI systems, right? Using the synthetic data, potentially, of course, typically with real data that we also have available. So it's really the mix of both. But we can also use it for validation, right? We can generate all sorts of critical scenarios and see how good is a certain system, can a certain system deal with such a situation, right? That's pretty much what we do with pilots, right? We don't just send airplane pilots to fly passenger airplanes, right? And maybe we do a test in the beginning and then let them fly for 20 years, right? No, that's not what we're doing. But they need to go back and they need to go into a flight simulator on a regular basis where they are tested that they know how to deal with all the critical things like an engine failure or all engine failure and really critical scenarios. They need to be able to respond to these critical scenarios, right, in their sleep, so to say. And that's exactly what we want to do for our AI systems, right? We want to make sure, we want to validate and then eventually certify, be able to certify that, yes, this system can deal with all the critical cases, and it's well enough to be sold and to be run on the street. Now, the last step is one that a lot of people forget, and I think it's critical to include this here, right? We really want to close this loop. And there's multiple reasons why we want to do that, right? For instance, if we have trained a car and this car sees something that it cannot interpret, it cannot understand, right? We want to certainly know about that, right? Because that probably means that whatever that car is seeing was not adequately either modeled or was not adequately simulated. At least it's something that didn't, right, is not represented in the car. And we have technologies to identify these cases. And we can use them to improve our models and say, hey, here's something that our models is not covering yet. But funny enough, right, even if our models were perfect, right, and we wouldn't have to do that, we would still have to close that loop, right, because reality changes, right? And so, yes, our models were perfect last year, right, but now we have, I don't know, e-bikes and lots of other things moving around the street that weren't there last year. People change their behavior and all sorts of other things, right? So our models are not perfect anymore. And so we need to adapt this model anyway. So, and we need to do this anyway because reality just changes, right? And we need to be aware of that, and we need to include that in how we build AI systems, right? Because they cannot be static, right? We're not static. We're constantly adapting our behavior to the reality that is changing around us. Now, it seems like I explained all of this in the context of autonomous driving, but this is really an approach that is very, very broad and applicable essentially everywhere where you can model the environment that the AI system interacts with, right? If you can model all the parts that an AI system interacts with in a suitable way, right, you can apply that approach. Right? There are cases where we cannot model this adequately. That's very interesting, but that's not the majority of cases, certainly not. So what can we do with that? And in interactive presentations where you would be sitting in front of me, I would now ask you, what are you seeing in this image here on the right? And consistently, very, very consistently, I get the answer, a person walking, right? And that's wrong, because all you're seeing is a couple of white dots moving on a black background, right? I think we can all agree on this. There is no person there. But however, you're right. On the other hand, you're right, because that data is derived from light markers attached to a person walking. And we're actually extremely good, right, to identify these patterns of white dots, particularly if they are moving, as the motion of a pedestrian, right, of a human. And actually, it's amazingly, we're amazingly good at that. So if you knew the person from which that data was taken, you have a high probability of actually being able to identify that person. And something I was really surprised when I learned this, if that data comes from yourself, then you would actually be able to identify yourself walking. Of course, you never saw yourself walking, right? Because your eyes are kind of sitting on top of this thing. So we actually have such a good feeling for how we are moving, how our body parts are moving, that we're able to identify our motion, even though from a point of view that we never been able to take, right? Well, maybe you walked in front of a mirror, but we hardly ever do that. So it's really interesting, right? How good we are to do this, and this is something that AI systems, computers can't really do this. So how can we teach AI systems to be able to have this high-level knowledge of information that, right, our perception is actually driven by the high-level models that we that we understand. And this is pretty much exactly what we try to do with AI systems today. And I have a whole set of slides that go into much more detail about that, but that's beyond what we can do today here. So here's a couple of interesting results we've been working on. So one example, I'm still showing this because even though it's a little bit older example here, but this is from, we actually kept, this is in front of the Computer Science building here in Saarbrücken. There's a zebra crossing. We have pedestrians, or actually students, I guess, walking towards the bus station, which is up the road. And we have two types of students. The one, they look backwards because the bus is coming. But they want to continue straight ahead. And there are those students who want to look backward because they want to cross the zebra crossing, right? And now for a car approaching that zebra crossing, it's really important to know whether, right, there's often many students walking there, to know, is any one of those students going to cross the zebra crossing? Do I have to stop or not? And as humans, we're extremely good at seeing this, right? There's hardly any conscious decision making here. We just see whether persons will walk across that or not, and you can actually see this in the data. If you look at the blue curves here, that's actually the rotation of the head, and you see that in both cases they pretty much turn the head the same way. However, the people here on the right, those are the people who want to cross the street. And because they need to turn their body anyway, they already start turning their body when they look behind them, right? So the shoulder and the hips already turn. And so there is a clear signal in the motion of pedestrians that identifies those people who want to cross, right? And this is the kind of signal that we want to be able to model in the motion of in these virtual environments, right? Because if we don't model that, our AI system will certainly not be able to pick it up, right? So we need to model this in an accurate way, and that's a very subtle signal. And then we need to train our AI system to actually be able to recognize this. So that's one of the techniques. I want to talk a little bit more about that link between AI and graphics, and I'll actually want to make the link here to radar simulation. So I've argued that I showed you that we do a lot of work on the optical, right, realistic rendering of camera of images, and at some point it became clear that the radar simulation is still not well done today. And in some sense, radar is very similar, right? It's also electromagnetic radiation, but it's a much longer wavelength. And so because of the longer wavelength and because of the fact that this is coherent radiation, we need to take wave optics into account, right? The wave effects, so interference, polarization, phase information, potentially diffraction, and others, right? And it's actually interesting what the relationship between optical rendering and radar rendering is. I don't want to spend too much time on this here, but it turns out some of the problems that are really hard in the optical area turn out to be really the key elements for radar simulation. We happen to work on a lot of those, which is caustic rendering specifically. And so a lot of the work we've been doing over the last years is actually quite relevant to the industry, to radar sensors. And we've been, just last year, we did a huge project, a fairly large project with the car industry of transferring this knowledge of Monte Carlo simulation to radar simulation. And this is now part of how radar sensors are being simulated and are being designed. So just to visualize this, because I don't have time to go into exactly what we did there, this is a very simple but very illuminating example here. Let me just, where's my mouse pointer? So if you look here at the lower left, right, we have a transmitter, we have a receiver, right, there's a street underneath, and there's two ways how the signal can reach the receiver, the direct way and the reflection off of the street. right? And on the right, lower right, you see what the signal should look like. So that's clear an interference signal, right? You have negative interference here between the two signals. And with standard Monte Carlo methods, actually already pretty good ones, much better than most of the radar, well, a lot of the radar simulations, I would argue. You see the results up there, and you see that, well, it doesn't match the signal as well. And then with a couple of techniques from that we've been applying here, so what we call texture filtering, path guiding, low discrepancy sampling, we've actually been able to improve the simulation dramatically. And actually, so give you some, so this is almost a perfect simulation, and we already know a couple of other ways of how we can improve that. But let me compare that to other tools that are available. So because you're probably not too familiar with that. So this is our simulation compared to measurements, actually our measurements, which is not the best measurements you can do, but it's pretty decent. And you see that the simulation actually matches the measured signal fairly well, right, in most areas. And we can simulate actually a 360 rotation of the object here in 33 seconds. Yeah, all of those simulations. So this is a commercial software that not only has a hard time even simulating the result accurately, but it even needs 13.4 hours, right? Not seconds, hours, to compute that result. And a comparison to recent developments in the radar area and the radar community. This is a paper we've been with people we've collaborated. You see that this is also fairly off in terms of the computation. So this, what I'm trying to say here is really that the knowledge of simulation, of modeling reality in computer graphics, and the way how we can simulate the sensor data, right, is really an instrumental part of developing safe, trusted AI systems, right? That's the message I want to get across here. And finally, since we're in the NHR context here, let me say a few words about our compiler framework, NEDSL, that we developed over a couple of years now. Where don't have time to go into all the details here, but essentially it's a novel compiler, a novel front-end language on which you can build your own domain-specific languages, or really libraries. We don't think you need a new syntax, right? It's new functionality, new interface, so new libraries are all you need, right? It's sitting on top of a high-level internal representation, which does a lot of the framework, a lot of the compilation step. The key element here is partial evaluation, which is built into the compiler in a very aggressive way. And the really interesting part is also that we can generate code for various backends, so for CPUs, for GPUs, now also for FPGAs and other accelerators. We're working on this now. So that's something that not a lot of compilers can actually do. In particular, we can do that in a way that it is performance portable. So you see this in a second. The same high-level code, which really looks like textbook code, is able to generate CPU code, GPU code, and FPGA code that in each of those areas is beating even the hand-optimized code of the vendors of that hardware. So in the traditional compiler, just to compare that, right, you have some source code that gets compiled. You have a program. Some of that input is static, so there's constants, there's whatever kind of data is encoded in your program, but then there's also dynamic data that comes from outside, right? And but the typical compiler, typical program doesn't take that into account. It takes all of that as input, computes an output. And what we're doing is that in the pre-processing stage, we identify the code and the input that is static. That can happen automatically. The compiler can do that with the right annotations. And during the compilation stage, the compiler takes that into account, evaluates the program. That's where the partial evaluation comes in, and generalize a specialized program where that static input has been taken into account, and so we only need to compute the parts that really depend on the dynamic data. We've tested this. There's a nice SIGGRAPH paper a couple of years ago where we've shown that. And let me just quickly summarize the results here. So this is on the CPU results. And roughly we get up to a 20% performance improvement of our system compared to the Embry system, right, which is the Intel high-performance Intel ray tracing, which has been really hand-optimized as far as possible by actually some of my PhD students who are working at Intel now, and then many more people at Intel. So if we compare that, the same high-level program on the GPU, right, we're actually able, if we use the same approach that NVIDIA of how to compute, how to implement the ray tracer, we use the same approach from NVIDIA, we're up to about 30% faster, right? And if we then switch to a different way of how to compute things, it's so-called wavefront approach, right? We can even get up to 40%, so between 30 and 40% improvement, essentially across the entire board, and that's quite impressive. Again, this is the hand-optimized code from NVIDIA running on their own hardware, right? And again, it's the same high-level code for CPU and GPUs. Of course, there's some low-level mapping that is different between the two architectures. And finally, we've also been able to run this on AMD. We don't have a comparison here, but it's right. This is the other thing, we can compile to different architectures for which those libraries are simply not available. So to wrap up, what I try to talk about today is in particular this notion of bringing symbolic or explicit compute models together with neural models. So right, using the explicit models of the geometry of pedestrians and so on, bring this together in many other aspects, bring this together with neural training of neural networks, and how simulation and high performance computing plays an important role here for AI. I try to show you that this digital reality, this four-step circular approach here is really a fundamental tool for AI, combining learning and reasoning in this continuous feedback loop. I talked about trusted AI, this need to actually validate how good the AI systems are, to provide guarantees. And my argument here is that we need a lot of high performance computing and simulations, in simulation and AI in order to really do this, in particular if we want to scale this up to all sorts of AI systems. But I also hope to convey the issue, all the issues. There's obviously big challenges ahead of us. Right, there's some promising results already, but there's still a lot to be done there. Right, I sketched this digital reality framework, but it's certainly not a finished result. We're working at different pieces of that, and we hope that more and more people are joining this. So I think there's a great future for combining HPC and AI, and we see this in many areas, that these areas need to work together much more closely on hardware, on software, on tools, and on applications. And with that, thank you very much for listening, and I'm happy to answer any questions that you might have. Thank you very much.
So thanks a lot. What is very interesting and inspiring talk, and pointing out that there's not either AI or HPC, but I think both need to work together closely. Both look in the same directions in terms of hardware, and they try to solve the same problems. So there's a question in the chat. How do autonomous driving AIs deal with sensor imperfections, noise, aging, damage? Can a faulty sensor, that means a lying sensor, be hazardous? And what do we do about it?
That's a really interesting and question that we don't really have a very good answer for. That's actually one. So we worked a lot on preparing a large project on trusted AI, which should really where a key part was addressing exactly that question. We had a hard time convincing the Ministry of really funding research in this area. That's something we're still working on. The issue here is there's a whole issue of issues here, a whole set of issues here. The one is, right, that an individual sense. So first of all, you want to make sure that there's some safety around the AI system, so that even that if the AI system does some mistakes, that will not be fatal, right? The other thing is really within the AI system that we can validate and certify the AI systems that it can deal with faulty sensors, right? At least certain kinds of faulty sensors. Ideally, can even identify if the sensor is faulty or not, right? Typically, there's not a single sensor. There's typically, right, you have cameras and radar, sometimes also LiDAR sensors. So there's actually a lot of redundancy. There's a lot of work on early fusion, right, where we want to fuse the raw data, or at least close to the raw data from those sensors with each other, right? And obviously at that point, any inconsistency between those sensors would be something that you could identify and say, hey, the left radar sensor is probably giving false results because that it's inconsistent with what the other sensors say there. So a lot of that should be built in, right? But I fear that not a lot of that is built in by now. So there's really a lot of work that needs to go into this. Another thing, just to say this as well, because it's one of the problems we're dealing with. The way cars are built is that the car manufacturers buy sensor from supplier companies, ZF and others, Continental and many others, and they typically, of course, they want to deliver as much processing with their sensor as possible. So actually, the radar sensors do a lot of processing within the sensor and only hand out high-level information, essentially about objects that they already have identified. So at this point, a lot of the raw information is already lost, right? And so that makes it actually hard at that level to really make this kind of error correction or identification of errors in the first place. It's already hard to do that. And so we are advocating for getting access to the raw data and do that fusion and also the cross-checking at that level, but this is kind of conflicting with the way the industry is actually working, and it's not clear how this will work out. Whether and also you then need to be able to do this with that radar sensor from one vendor with the camera from another vendor, and then they change the vendor, right? They change the supplier, and the whole system still has to work, which is something that neural networks are really bad at right now. So modularity is not something that's typically built into neural networks, right? So we need to design our system such that, yes, we can change that radar sensor to another one and have the whole system still work. So there's a lot of practical issues that need to be solved here. So very good question, Mr. Hager.
Well, thanks a lot. Are there more questions? So if I cannot see the, Mr. Lork, he has a raised hand, so please speak up.
Yeah, hi, thank you very much for this very interesting talk. It was very inspiring.
Thank you.
I have a question about this 4-stage loop, or when it has 5 stages. Can you explain a bit how to select the important training examples out of the millions of possible situations that can happen in the real world? Should it be those training examples that are of very high cost, like if they produce a fatal accident, or should it be training examples that are very difficult for the machine to solve, like a dark figure in a dark environment?
All of the above. This is really one of the questions that we and others are working on right now. It's even worse than what you already mentioned. First of all, we're dealing with a very high dimensional parameter set, right? There's hundreds, if not thousands, of parameters you can modify, right? Where is the human? How is he moving? How is he configured? What does he look like? And so on. Human pedestrian, let's say. And then there's many pedestrians. A lot of data that we could modify. And what we care about is the critical situation. Of course, we have a lot more information than just a bunch of thousands of parameters, where we have some high-level information that we could use. So, I mean, like if the kid is 500 meters away from the car, then right, we kind of know that nothing can happen. But the ideas that you have are already very good. So at the end, what we want, right? If you think about that pipeline, right, and there was the scenario on the top left. Top left, and then the generated data in the bottom right, right, and you have this configuration, and then you have the simulation. And only then do we apply the AI. And now the AI, right, what we want is we want the best data to train the AI. If we focus on the training, right? We want the data that gives the best training, right, moves the AI system into the right direction. The best training results. And that's not entirely clear of how to best do that, right? Because you cannot have derivatives all the way back. At least that's very hard in many cases, but that's something that would be very helpful. It's also about a sampling procedure, right? Of characterizing that space of all possible configurations, and identify those that would again have the best training result at the end. And so we could build this, and a lot of Monte Carlo simulation technique actually work exactly in this direction. So a lot of what we're doing on the graphic side is applicable here as well. But it's even worse than that, right? Because once you have identified that, I don't know, for instance, I mean, just to make this more concrete, let's say the AI is confusing, I don't know, a bicycle and a motorbike, right? It can't distinguish between the two, right? Or has difficulty doing that. So we can use that. Right? There's confusion matrices that you can build, which says which objects are misclassified with other objects. So we can use that, for instance, to say, hey, we need to generate more images that have motorbikes and bicycles, so we can kind of refine the training that the AI better can distinguish between the two, right? But once we've done that, right, then at some point, hopefully the AI has learned to distinguish bikes and motorbikes. And then we need to move, right? Then we need to move. So it's a dynamic scenario. We need to identify that, hey, we now know about bikes and motorbikes. Now we need to work on some other aspects, right? And this needs to automatically and be adapted, right? Adapt to what we already know, what we've already learned, and what we've not learned. So that's a non-trivial process of how to do this, and that's still right. We can do some work in this direction, but it's not as optimal as we wish it to be. And there's a lot more that needs to go into research to optimize that.
Thank you.
Okay, thank you, Tobias Huth.
Yeah, thank you very much for this interesting talk. So the simulation can never be perfect, and the AI might be sensitive to errors introduced by the simulation. For instance, we had the problem that the AI was really responsible on the noise that we have simulated. So what can you do about this?
Well, there's many techniques who you can deal with. The one is you do a refinement with real data, right? So maybe you learn. I mean, there's many ways you can do that, but one is you train with both data sets and do some refinement with real data at the end. So kind of domain adaptation in a certain direction. That actually works reasonably good. There is obviously the direction to improve the quality of the simulations. Right, there's if it's noise, right, there's really good denoising algorithms now on the rendering side, right. They might generate some artifacts that the noise could be sensitive to as well, but at least the noise is gone. So that's something we haven't tried yet, but I'm sure this will help a lot. And then there's right, adversarial training or right, you can train the AI not to see the differences between those images, right? So essentially have a discriminator that creates a loss that punishes the differences, recognizing the differences between real and synthetic images. So and what is the best, right? Well, there's another point I want to make here is, right, the image doesn't necessarily have to look nice, right? Because it's not meant to be looked at by humans, right? It needs to be good for the AI that looks at these images, right? And that doesn't necessarily mean it also has to look well for humans. That's an interesting aspect that I think a lot more research has to go into. And there's this interesting question I ask, and let me point this out here as well, right? I mean, at some point, I'm arguing we might actually be generating more images for AIs to look at than we're generating images for humans to look at. Right, in the past we did, right, the film industry and so on, we generate images were essentially only meant for humans to look at. And we really see that shift. Now, again, we still do that, right? And we do this a lot. But it's interesting that if this really takes off, that we generate synthetic data for AI systems, I wonder when we reach a point that we're actually generating more images for AIs to look at than we do for humans. Just an interesting thought experiment.
Yeah. Same for our lab. We are simulating more data than we are actually recording. Thanks.
Yeah, exactly. It's the same thing. Exactly.
Thank you.